Okay, now it's working. Good morning, everyone. It's very nice to see all of you. Thanks a lot for coming. And welcome to the first, I have to read the name, ELLIS Madrid Winter Workshop, Bright Minds Cold Days. Okay. We have, well, I don't know if today we are starting a tradition, but, well, it's very nice to have it organized at least once. Okay. So today we are gathering an amazing group. We have great lectures, but also many researchers from around Madrid and beyond. Actually, we have many more posters than, or some more posters than space. So going in the opposite direction like the big venues. So we will try to figure out later how to organize it. And well, and many old friends that are visiting us before taking their Christmas holidays. So thanks a lot for joining us. Also, thanks a lot to Patricia, Isabel, and Igor for the logistics organization of the whole event. Well, let's hope that we all have a nice morning together. So let's jump to the first speaker. It is my pleasure to present Finale Doshi-Velez. I'm going to read the bio. So Finale is the Herschel Smith Professor at Computer Science at the School of Engineering and Applied Sciences at Hardvard University. She leads the Data to Actionable Knowledge Research Group, working on probabilistic models, interpretable machine learning, and reinforcement learning, especially focused in healthcare and human-centered domains. I had the pleasure of enjoying with Finale a few days recently in Peru for the Machine Learning Summer School. Not only me, a few also of the students present today. We enjoyed her lectures very, very much, so we didn't want to miss the opportunity to invite her again, especially because she's been around Europe for this semester. So Finale, thank you very much for accepting the invitation, and the floor is yours.
Thank you all so much for inviting me. So today, I'll start out by mentioning, I do work on, quote, serious applications. My history, I started out working on robotic wheelchairs during my PhD. I did some Bayesian nonparametrics during my master's, and then during my postdoc, and since then I've worked mostly on healthcare applications, real data, trying to figure out what's good for people in the clinic, what treatment, what patient, all this very useful stuff. I'm mentioning this just because if people at the posters and stuff want to talk about, impact and all of this, very much game. But for the next hour, I would like us to maybe take a break from all the serious stuff to enjoy or think, invite everyone to enjoy or think about this one parameter in reinforcement learning called the discount factor that I feel like is just not getting enough attention, right? So I invite you for this talk we're going to have fun. Getting a chance to think about something that maybe very few people in this room have probably spent time thinking about. I did not spend much time thinking about it until we got a set of things in this direction. I also start by saying, as I say for all the talks, I just love being in person. It's amazing to be here. And so it's like the post-pandemic glow does not wear off. So please feel free to interrupt with questions, anything along the way. We are here to be interactive. That's why we're all here in this room physically at the same time. Okay, so for this talk, probably most people in this room have heard, actually, raise of hands, like people have heard about Markov decision processes sometime. Yes, okay, great. You've probably seen and read somewhere, Markov decision process is defined by this tuple SATR gamma. And for people who are not so familiar, that's okay. Again, ask questions. But S stands for the state space, so it's like where you are now. The action is what you decide to do. The transition is what happens when you take the action. And then the reward is like what you're trying to get to in the end, or what rewards that you get along the way for every state action pair. So that's what we usually think of when we think of a Markov decision process or reinforcement learning problem. And notice here that I have defined S, I've defined A, the actions, I've defined T, the transitions, I've defined R, the rewards, but there's this one sad discount factor that is missing, right? And in fact, when we do our research, we decide what the state space and the action space say we have this robot, the state is going to be the location of the robot, the action is going to be what we put the motor, voltages into the...
Can you use
Oh, sorry.
Thank you.
Into the robot. And so we decide on the state and action spaces. You need to turn it on. Hello? It's the light is on. Oh, do I just need to stay closer here? Okay. Oh, now it's on. Okay, great. Okay, this way I can point to the screen. Okay, so we set up our state and action spaces. Usually, then we spend some time learning the transitions and the rewards. That's the part that we don't know. So we try an action. We say, okay, we put this voltage into the robot. How far did it move? That's learning our transition function. And then we solve. And what do we mean by solving? Well, we want to find a decision-making strategy, a policy that will maximize our sum over the rewards that we're going to get over time, discounted. So this is where the discount factor shows up. Because a discount factor, which is a number between 0 and 1, is telling us how much we care about current rewards versus future rewards. So if you imagine that this discount factor here, gamma, is equal to 0, then we would only care about the reward that we get at the first time step, at t equals 0. But if this discount factor gamma was equal to 1, then every reward we get along the entire sequence would be equally important. So that's what the discount factor is doing. But notice it really doesn't show up. Initially we do some definitions, we do some learning, and then we just kind of toss that all in, usually, into our solvers. But as I said, we rarely spend much time thinking about the discount factor, but today we're going to let the discount factor be the hero. We're going to spend all day talking about this one number between 0 and 1, or all hour. All right. So we can think of, one way to think about the discount factor is the probability that you survive until the next time step. So if you are sitting at this, at t equals 0 right now, and the discount factor is equal to 1, you're fully confident you're going to survive for the next time step. If the discount factor is 0.5, there's 50% odds that you're going to die in the next round. You're not going to be able to get future rewards, right? So that's one way we can think about it. But it's a way to express how quickly we want the rewards. And one thing I want to emphasize is that usually when we think of reinforcement learning, we think of the transitions as the world, right? We don't get to choose how the robot moves when we put the voltage into the machine, right? That is just the physics of the robot. But we do get to pick the reward, right? We get to pick what we want the robot to do, for example. And one thing I want to emphasize is that just like the reward, the discount factor is made up. It doesn't exist in the world. It's something that we choose to say, how quickly do we want to get the rewards. And when our models are approximate, one thing that I'm going to spend most of today talking about, it can also prevent us from overfitting. And so what does overfitting mean in reinforcement learning? So first I'm going to start out by sharing some work from some other labs, some really interesting work that's been done. Actually, first, a little bit of intuition. Right, so let's suppose, what do I mean by overfitting? So let's suppose we have our agent, we have some real reward out here, but because of the learning process, learning is not perfect, and so you start hallucinating rewards that don't exist. So you're pretty sure about this one, but maybe you also hallucinate that there's some other rewards that are also out there, right? Then if you hallucinated those rewards and you have a really sophisticated planner, right? Very sophisticated decision-making strategy, then you might decide on a path that goes through everything because you are able to think that clearly, right? You are able to think about, I want to have a complicated path that will get me every single reward. But by doing so, you end up overfitting in a way because you go to all the hallucinated rewards as well. Whereas if you were forced to have a simple strategy, maybe you would skip the hallucinated ones that have low value, right? If you thought this one is worth 10 and you thought these are worth 1 or something like that, you don't bother extending your path to go for these little tiny things that end up being non-existent. So in this talk specifically, I'm going to consider what we call the certainty equivalent setting. So in this setting, it's a fancy word. I feel like there's too many fancy words in machine learning. All we mean is that we're going to take the data, we're going to learn T, and we're going to learn R, step 1. Step 2, we're going to use that T and that R that we have learned about the environment to solve for policy pi. Pi is our decision-making strategy. So that's all, right? It's kind of the simplest thing you can imagine doing. Take the data, learn the model. Once you learn the model, you optimize with respect to the model. Some recent work have observed that decreasing the discount factor is equivalent to decreasing the complexity of the allowable policies. So let's just think about that for a moment. So if your discount factor was 0, because I said this is a thinking talk, right? Like encouraging everyone to spend some time enjoying thinking about something perhaps new. So if your gamma was equal to 0, you know, the policies you can consider are really just one step, right? Because at every single state, I'm pretty sure I'm going to die the next round, right? I'm sure I'm going to die the next round. So all I can do is select from the actions that I have, right? There's not really much thinking ahead to be done there. All you have to do is just select the best thing you can get right this minute. Whereas if the discount factor is long, right? If I think really far ahead, now I'm thinking multiple steps, right? Like I'm going to take this action, it will get me here. Once I get here, I will take another action, it will get me there. And so the space of possibilities that I'm thinking about is growing, right, as the discount factor is growing. And that is the way in which these two are related to each other, right? The complexity of the policy and the value of this one simple number between 0 and 1. So this is the works, again, not our work, but these prior works that have explored this thing. And what they observe is that in a number of environments, let's say here's your discount factor, you can set it between 0 and 1, as we've said, that depend, like especially when you have very few samples, as you increase the discount factor, your training loss goes down, but you know, your test loss, you know, has this curve because at some point you start planning for hallucinated stuff because your model's not quite right. You had some data to learn that model's not quite right, you're overfitting to hallucinations. And as you get more data, this kind of effect goes away, as we would expect for overfitting, because now we have learned a reasonably good transition model. We don't have this issue anymore. And other works have found that other ways of limiting the policy network helps as well, but have, again, seen a similar sort of curve as the amount of data increases, you know, not an issue. But when you have very little data, you have this U-shaped curve. And notice like the bottom of the U is lower for lower number of trajectories and you know, goes up for increasing number of trajectories, as we might expect, because increasing the discount factor means that we can plan further ahead into the future. Okay, so first question that we asked was that, okay, these other works have shown that thinking carefully about the discount factor and its relationship to overfitting can help in the reinforcement learning case, the forward planning case, right? But what about in inverse reinforcement learning? So in inverse reinforcement learning, we're watching people do tasks, and we're trying to figure out what is their reward function, right? What is their subjective part of their reward? So I mentioned at the very beginning, hey, I also do like, you know, real applied stuff, as well as this, you know, fun math stuff. So, you know, this had a real place where we started, which was we look a lot at healthcare data. And when we work with healthcare data, we're just watching what the clinicians do, right? We're not going to be allowed to just go in willy-nilly into the ICU, the critical care unit, and change up, you know, what the policies are and learn by chance, right? We get all the data. We're trying to infer what the doctors actually care about. And because if you imagine going to a doctor and say, please give me the exact function that I should use for my reward, they're not going to be able to do that, right? So you watch and you try to observe and you match. So inverse RL is like a problem that I care deeply about for these reasons. And a natural question was, when it comes to the discount factor, you know, is there a similar effect? Okay, so now we get some math. So we have some expert trajectories. So these are the trajectories that we observe in the data set. And let's say for now we assume that these come from, this is an optimal policy, star for optimal policy, with respect to like their true reward and their true gamma, right? Whatever the experts feel like in terms of how much of a rush they are in. So the goal now, instead of just inferring R, we're going to try to infer R and gamma. We don't see either of those. And we're going to try to infer an R gamma pair that minimizes this particular loss. And what this loss is saying is that if we run a policy with the real R and the real gamma in a world with the real R and the real gamma, what's the value we collect? And the value just, in terms of cheat sheet right here, is just the amount of rewards, that the discounted rewards are objective over time. So, and we subtract out, the difference is now the value associated with trying to optimize with respect to our learned R and our learned gamma with respect to the real world. So here we are always testing with respect to the real world, but in one case we learn the policy with the true parameters of the expert. In another case, it's our guessed parameters, and we want to minimize that loss between the two. So reasonable sort of thing to do, right? We're saying what matters is like if we were to use this reward to optimize, how well would we do compared to the expert. Okay, so this has a bunch of math, but I will walk you through the key part of it. But in this work, what we proved is that let this capital pi be the size of the policy class that is induced by using a smaller, discount factor. Then this thing that we cared about, this is the same thing from the last slide, right? So I said, I just tried to convince you this was a reasonable loss function. So this loss function is bounded by two terms, the sum of two terms. And this first term is the error when we're trying to estimate the reward. So if we, because we're watching the experts, we only have n examples of those trajectories, those actions that have taken, we're going to have some approximation error. So how wrong is our guess of R going to be? That's what this first term represents. And importantly, it grows with the size of the state space because there's more R's to, more stuff to learn. And it also grows with the size of the policy space. That's the important part here. And then the second term over here is the optimization error. So once I get the R, now I have to optimize and find the best policy with respect to that reward function. And if I don't do a great job of optimizing, then I also will do poorly, right? So not only do I have to find the reward, but then I have to optimize with respect to the reward to actually find that policy, right? And what this is saying is that it grows depending on the difference between the true gamma, the expert's gamma, and the gamma that we happen to use, which kind of makes sense because if the expert is thinking really far ahead and we are not thinking very far ahead, then we're going to incur some error, right? We might be solving with respect to the exact same reward function, but if I'm thinking only a day ahead, I'm like, let's eat those cookies. And you're thinking, 30 years ahead, and you're like, don't eat the cookies, right? We have the same reward function. we enjoy cookies, but we want a healthy life, but you're thinking further ahead, right? So there is an optimization error that happens over here if the gamma is wrong. And so these two terms are competing with each other. Yes?
Another question is whether the true policy has been computing, assuming that the discount factor decreases exponentially with time. Maybe the true model is assuming a discount factor that doesn't decrease that fast.
You mean, so we're always assuming an
gamma to the rest of the things, maybe the discount factor doesn't follow that law.
Oh, I see. Okay, at the very end, I will mention like humans are hyperbolic discounters often. They're not exponential discounters. For now, we assume that everyone's an exponential discounter. Yes, fair point. Okay, so this suggests that there's an intermediate value that will give better performance. Okay, so does this actually happen, in terms of simple examples? So we look at some simple examples, and what we see is that as we get more data, the error that we get if we use the ground truth in blue is higher than if we use what would be the optimal discount factor. So if you use the theorem to find the lowest, the gamma that gives you the lowest value here, you get a lower error rate. Of course, if you collect a lot of data, then those things kind of converge. So that makes sense, right? It makes sense how we expect to see it. The other thing that I note is that you can't solve the stuff in this theorem all directly. You have to do a bit of, because you don't know the actual transitions, you have to plug in various elements. So if you use cross-validation to find the best plug-in estimator, here is the error versus ground truth, so we're getting better and better. So this is how much worse the ground truth is for an estimated version. And also the difference between the oracle and the estimated, what's physically possible or possible to compute. So basically what I'm telling you here is that, yes, we had a nice theorem, which had some things that we could not compute very easily. But in practice, there's a practical version of this computation that also does reasonably well with respect to this metric. That said, is it gorgeous and beautiful? Not quite. So this is a talk that you can give after tenure because you can leave questions open, right? Do we see dips, right? So this is gamma along this line, do we see that there's an intermediate gamma that often performs better than either end? Yes, we do, which is interesting. But the values are not clean, and it varies a lot depending on specific environments. I don't expect you to make sense of these, but pointing out that there's a lot of stuff additionally that's going on. The previous plots that I showed you from the other papers averaged over lots of environments, and that's where you get the nice curves. And if we average, we get pretty looking nice curves also. But just pointing out that there's a lot of detail that goes into this that is still a bit of an open question, which I think is quite interesting. Okay, so that was, again, motivated by, hey, we're interested in inverse RL problems, especially in these sorts of health settings. And we found this cool result that just like in forward RL, limiting the number of policies when you think in the inverse RL setting, just this one factor, right? It's just one number, gamma. Changing that one number can improve the quality of your inverse RL. It's pretty cool. Then the natural question we had is that, well, our hospital data has trajectories from multiple experts. What if they don't have the same planning horizon? So again, you and I, we're both working in the hospital. I see the blood pressure is dropping, and the first thing I do is like, okay, let's flood the patient with fluids. It will raise their blood pressure. And you're thinking a little further ahead, and you're like, no, if we flood the patient with fluids, it'll accumulate in the lungs. We're going to have to deal with that. Tomorrow is going to be bad. We both have the same goals. We want the blood pressure managed. We also want the patient to survive this hospital stay. But one person is thinking a bit more ahead than another. So this is a hypothesis, right? In real data, it's probably also the case that different doctors have slightly different goals, right? They might say that blood pressure is very important compared to urine output. And someone else might say, no, like creatinine levels are really the thing that really is important to me. So this is a simplification, right? This is saying simply, what if we think that the trajectories come from multiple experts? How do we manage, what can we do if they have different goals but different, if they have the same goals but different planning horizons? So let me now, again, put up a little bit of math, but walk you through it. So if we're doing inverse reinforcement learning, in the previous version, I didn't have to go into any details of how it actually works, but there's a couple of different ways to do inverse reinforcement learning. One popular way, one of the first ways that inverse RL was done, was to say, let us find a reward function, and in that reward function, that was a mistake. So what we want to make sure is, first of all, let's say the experts are, so pi star is the policy that the experts are doing. So if you're in the hospital, that's the actions that the doctors are taking that they actually took, that we see in the data set. So here's the action that the doctor took. If we take that action, take the value of that action. So again, cheat sheet down here. What is a Q function? It's the value of taking a particular action in a particular state and then following some policy afterwards. So down here is our cheat, but you can think of it as how good is it to do this action, roughly speaking. So Q measures how good is it to do this action. Well, it had better be, if we think the doctor is optimal, it had better be that the doctor's chosen action, pi star of S, so the action that they choose, is at least as good as any other action. So for every other action A, the value of the doctor's action must be more than or equal to the other choices. So that's our constraint over here. And then the thing that we choose to optimize, we have some choices here. Like the thing with inverse RL is that it's ill-posed. There's a non-identifiability in the problem. So what do we decide, or what is one reasonable thing to do? We say, take now that best action, the one that the doctor took, subtract some other action choice. So that difference, which we know is greater than 0 because of our constraint, let's try to maximize the minimum distance between those two choices. So, between the best action and the second best action, let's try to make that gap as big as possible. That's what this objective function is saying. So it's a reasonable choice, right? Again, because the whole thing's non-identifiable. So here's one option that you could take. So now let's suppose we have the multiple experts. And the multiple experts are going to have multiple gammas involved, right? How can we change what I just explained over here to be more, to allow for multiple experts? Well, what we could do is we could say, okay, we're going to sum, let's say we have k experts. Let's sum over the experts. And again, just try to seek out the difference between the expert action and the second best action. Same idea, we just add in one more summation, and we try to say we're going to try to maximize the min difference summed up over the experts. It's a reasonable decision, right? There was kind of some arbitrariness into how we did this, but unfortunately this version does not quite work. And the reason why it doesn't quite work is that this summation kind of hides situations or allows situations where this difference ends up being 0, right? Because if one difference is really big, right, then the other differences could be 0, and this maximizer over here won't know the difference, right? If we have 3 different experts, it might say I'm going to maximize the difference for the expert number 1. Did a great job, and I don't care about any of the other experts. And this is exactly what we see, in a small toy example. So in this toy example, there really is only one choice to be made. You start at S0, and from S0, you have to move to one of these other, you get to choose an action that takes you to a different state. Each action has a different probability of success, or you just stay at the same location. So what that means in the real world, maybe I should come to this side, is that what that means is that if you're in a rush, you go straight and get your +10, right? If you're in a rush, what does that mean? That's a green line here. So if you're in a rush, if your gamma is small, because it's all about gamma, right? If your gamma is small, you go straight to the end and collect your +10. If you are less in a rush, with 0.9 probability, you can go through this route. You don't have to take too many tries to go through this route. So that's this orange policy over here that says go through S1. And if you really have time, to kill, then you're like, what, this action only succeeds 60% of the time, so it might mean that 40% of the time I'm still stuck waiting here. But I can just keep trying until I collect my +7 and get my +10. So that is this blue over here, that if I have time to kill, then I will wait, right? If my gamma is large, then I will keep trying so I can get the 17 reward. So that is like this really toy scenario. And what we find is if we use the previous optimization, so these are the 3 different experts that we observed, then everything kind of collapses. And it puts zeros up here and when it's trying to learn the rewards which is wrong, right? It doesn't make sense. Doesn't make sense also because if we have different experts with different gammas, if they're in a different rush, that should help us figure out what the reward is, right? Because if you saw you and me, go back to like the dieting example, right? And I go for the cookies, and you decide not to go for the cookies. And we know that we have the same reward function. The only thing difference is the gamma. Then we know that that you value cookies. You have more self-control because you're thinking about the future. But we that is told the world that cookies are valuable, right? So having two different discount factors actually teaches us something, or should. Having us three should teach us. But that previous version didn't actually solve the problem. Now there's a simple fix where now we look for the worst case over the gammas, so over all the experts. So rather than having a sum over all the cases, we're just looking for the worst case scenario. And we want to maximize the gap for the absolute worst case scenario for situations where the actions differ. So it's a very small change. Kind of, in some senses, might feel obvious. But it does let us learn a policy structure that looks similar to this one. Again, there's some non-identifiability, so they don't match exactly. But overall, they get a similar structure of pattern. And I'm putting this out there, because as I started this talk is not meant to be, oh, we're going to solve major problems in health or something like this. But just like, isn't there so much like cool, weird stuff that happens with this one, discount factor? And so there's open questions here, of how to use this how to continue to extract stuff from this non-identifiability. If you look at our RLC paper, we also have a lot of subtleties and duality things that come up if you're using max-ent versions versus linear programming versions of IRL, which again, one of those things that we never realized that all of these things kind of existed until we started thinking, well, what if we want to solve with multiple discount factors? Okay, I'm going to kind of skip through this. It just shows that, yes, it works on examples. Of course, there's an open question, as I said at the start, about how much behavior variation comes from differences in goals versus differences in discounts. Okay, so the last technical section that I want to go through is actually returning back through the forward RL problem. So I spent some time talking about inverse RL. And now I want to say, okay, we love the discount factor because it's one number. I love the discount factor because it's one number. But maybe it's really not enough when it comes to penalizing, thinking too hard about certain futures and all of this, right? Like in terms of preventing overfitting, can we make it just a little bit more complicated and get even more benefits in terms of these overfitting issues? And this work was, again, inspired by situations where we have really low data and we have relatively hard compute constraints. So one application area that I also work in besides these sort of clinical settings is in mobile health. So in mobile health, people have their phone. They're getting nudges on their phone to remind them to exercise or to take their medications or these sorts of things. And you just don't have a lot of data per person because each person is distinct. And you don't have a ton of compute. Either the compute happens on the phone or needs to happen in this relatively short exchange with some cloud server. So you're trying to think of simple algorithms. Also, complicated stuff is probably going to break. It's probably going to overfit. Right? But we want, so again, trying to emphasize, we want simple solutions, but can we make it a little bit more complex to help us out? So now we're going to go back to the forward reinforcement learning setting. So here I've learned a transition function. I'm trying to solve for an optimal policy with the transition function I've got. So TMLE is going to be like T maximum likelihood estimate. So it's just the simplest thing you can do. You've got some data, you just fit the model to the data, right? Maximum likelihood estimator. And then those previous works that I showed you at the very beginning of the talk, they said, take TMLE and then use a different discount factor, right? They said use a smaller discount factor, and that'll simplify the set of policies that you're going to consider, and you won't overfit if your transition function has some errors in it. That was the idea that they had. So the first thing that we observed is that what does it mean to plan with a smaller discount factor, right? Well, one intuitive thing that I already told you is that it means that we don't want to have such large space of policies. But another way we can think about it is that let's imagine that planning with a smaller discount factor effectively changes your transition function. So my new transition function, with smaller discount factor, is equal to is a mixture of 1 minus epsilon, the maximum likelihood estimator, my originally learned function, plus epsilon times zeros. And this kind of makes sense because remember at the very beginning I said that the discount factor is like the probability that you die, right? Or that you survive. So 1 minus the discount factor is the probability that you die at a particular round. And adding in, so now this no longer is like a legit probability distribution anymore, right? Because this thing was legit probability distribution, the transition function. But now I've added in, mixed it with some zeros. But what do those zeros mean? It basically means that you leave the system, right? It means that you die. So when you plan with a smaller discount factor, what we're saying is that you go with the original thing most of the time, but some of the time you just kind of leave the system, right? You don't exist anymore. That's what we're kind of intuitively saying with this equation. And what is that epsilon? Well, the epsilon depends on the real discount factor gamma and gamma p, which is your planning discount factor, the fake one that you use. So what we're observing here is an equivalence between decreasing the discount factor and planning with a different transition function. And that's going to be important in the next slide. So that's just like idea number 1 here that we're going to have to use. Okay, so now here's a completely different equation, but they're going to connect to in the next slide, I promise, or 2 slides. So let's consider a very different way of solving this problem, right? Instead of lowering the discount factor, I'm like, I am going to be Bayesian-ish. Okay, I come from, okay, during my master's and PhD, I was taught that being Bayesian means taking integrals and, just like taking the mean a posteriori estimate is not being Bayesian, that's being Laysian. But let's suppose that you're going to be Laysian here. And what you're going to do is you're going to say, I have some prior over the transitions in a discrete setting. This would be a Dirichlet prior over your multinomial counts. Then what is the maximum a posteriori estimate of the transition function? Well, it's going to be a mixture of your maximum likelihood estimate and your prior. And so if you haven't done any stuff with Dirichlets or multinomials or Bayesian stuff, that's fine. But basically the solution ends up being a mixture, again, of the MLE and something else. In this case, if you're following the Bayesian approach, the epsilon over here turns out to be this big, messy business over here. But the important thing, actually, I should stay in the middle. So the important thing is that these alphas are alpha set from the prior, and the C's are the counts. So what this is saying is that if you do a lot of visits to a particular state in action, then the epsilon becomes really small. You get rid of the prior, you trust your maximum likelihood estimate. So that's basically what's going on in this equation. But you notice that the form of this equation looks very similar to the form of the previous equation, where we're decreasing the discount factor. We're planning with a smaller discount factor. So a natural thing is, well, is there an equivalence, right? Because we can write both of these ideas now in terms of mixing the maximum likelihood estimate with something else. And indeed we can. So what we find is that if we put those together, then the Bayesian prior on a particular state action pair looks like the following. Like it depends on the gammas over here, and then it depends on these counts over here. So this is what happens if you set those epsilons equal to each other and do a little bit of, munging back and forth. And this thing is really odd for the following reason. This equivalence, this bit over here, fine. But what we're saying here is that places that you visited a lot, end up kind of increasing your alpha. That's a little odd. And also that if you have a smaller discount, you have a larger prior weight. So like basically this is saying that we're going in the opposite direction, right? That if there are states that you have visited a ton, then having a constant discount factor, like let's say we set this, wow, okay, sorry. Let me say this one more time a little more clearly. Let's suppose you set this thing to a constant, right? Because you have a Dirichlet that's like just uniform across the board. You don't have any preferences for the sake of argument. For places that you visit a lot, right? That means that you want this term to be smaller, right? That means you increase the, decrease the discount factor to make this guy smaller. Because the smaller this number, the bigger this whole number gets. So it's going in the opposite direction. It's basically saying that if you use a uniform discount factor, you're penalizing the states that you visited more, right? And that's weird because from a Bayesian perspective, if you visited a place often, you should trust that more than if you haven't visited a place often. So it's going in the wrong direction. So what we do is that we say that we can actually solve for the optimal epsilon and for each state. So ij representing the state. The details here don't matter a ton, except to note that it does involve the true transitions, which we can use a plug-in estimate. So on the next slide, I'm going to show you what happens in both cases. Okay. So first of all, we note that if you have a discount regularizer, using discount regularization, so I'm going to use a smaller discount factor than is reality. I can convert that into an epsilon, and I can see how well I do on my task. That's my task loss over here. And I can place a uniform prior that's kind of matched. What I mean by matched, I mean matched over here, right? So if I match it, they do exactly the same when all state and action pairs are visited evenly. So when I have completely even visits, these things match up, and it has a nice U shape. So our results are not invalidating things that people have seen in the past, but I'm pointing out this important thing of like when SA are visited evenly. When they're visited unevenly, which is like kind of almost always the case in reinforcement learning, do you actually go to every single state, transport yourself to every single state and you try every action? No, you don't. You're following trajectories. The trajectories are going to have you spend more time in some states than in other states. Then what we find is that if you use the discount regularization, in general you're doing worse than a uniform prior that's matched. You still are, again, you still have this nice shape, U-shaped curve, and you can get benefits, right? You can decrease your loss by being smart about it. But now if you're state action specific, well, if you use the oracle value, so you don't need a plug-in estimate, if you had the two transition matrix values, you can do better than all of those. And then if you have to use the plug-in, okay, sometimes you do better and sometimes you do worse than the uniform prior, but you're almost always doing better than the discount regularization. And it's one number, right? And now you don't have to search because in practice, every epsilon choice here gives you a different policy that you have to choose from. So once you solve for different epsilons, what do you do? How do you choose which one? And in our approach, you don't have to choose which one. You just go with the one that's the best. All right. So this is pointing out that as much as we love, discount regularization, And I think it's just such a cool idea. Like the first time I saw this idea that just by changing the discount factor, you can reduce overfitting in RL, I thought it was like the coolest thing ever. But it does have limits, and being able to penalize based on your state action pair, specifically saying that, hey, I visited you a lot of times, you don't need to be discounted a ton, whereas I haven't really seen you very much, you need some more discounting, can be very helpful. Okay, so we've done a lot of hard work. I've forced you through 3 steps of like mathematical arguments in less than an hour. I'm going to just mention one last fun thing that we've been working on that has no math attached to it, but relates to the, again, cool stuff with the discount factor. So this is just a few of the fun things so far. But as I mentioned, we're interested in this idea of mobile health as one of the applications in our lab. I mentioned this a couple of times, this idea of like, you know, sometimes we have goals, but we just don't think far ahead enough to reach our goals. And one thing that we are exploring in our work is, let's say you're trying to do some frictionful task, like you're trying to learn a new language, you're trying to do an exercise program or something like this, something that's no fun in the moment, but you will value later because you did it, right? How can we encourage people to stick to their program, right? Stick to doing the study, stick to doing the flashcards, stick to doing the exercise. Well, we imagine that there's people who have, there might be 2 distinct reasons why you're not sticking with your program. One of them might be that it is just too freaking hard to do the thing, right? Like whenever you exercise, you get all sweaty and gross, and it's miserable, and you just hate it, right? You don't like the way the clothes cling to you and all this, right? I'm not in this category. I don't get it, but I don't get why people don't like getting sweaty. But you know, I believe that people such exist. So that's like having a really high burden, right? Like doing the task itself is really difficult. For other people, it might be that you just don't see the point, right? Like I have been exercising, I have been doing my flashcards. Like, is this ever going to make a difference, right? You don't see the point. You don't, and like I'm giving kind of silly examples, but this happens a lot in rehab. So, you know, you have these elderly patients, they've had a major surgery. They need to do some sort of exercises to get back, into, you know, moving and stuff. And they just, it's not like the exercise is terrible, but they just don't see where this is leading them. And so the idea here is that not only can we give people rewards, right, which is a typical way of thinking about how to handle difficult tasks. Like, okay, every time you exercise, you know, here's $1, here's a cookie, or something like this. But another way is to change people's perspective in their planning horizon. So things that have been done, for example, in the literature, like imagine being able to go to the playground with your grandkids again. Right? By doing this exercise, you're going to be able to do this other thing that you really want to do. And what that's doing is it's increasing gamma, right? The subject of this talk, right? So we imagine that there's a set of activities or set of interventions that increase the user's discount factor. And that our nudges can either provide rewards, like here, have a cookie, or they can say, you know, you should really do your exercise because, you know, you have these goals, you know, that you're aspiring towards that are really meaningful to you. And we find there's different types of interventions for different types of users. So there could be someone who's not thinking far ahead and also just like doesn't like the activity. And for them, there might not be a lot you can do if they are pretty, you know, they're far from their goal. And as they get closer to their goal, maybe you can encourage them if your goal is in this direction, SG, to get there. In other cases, you know, maybe they don't mind the activity so much, but they're just not thinking too far ahead. And then from pretty early on, you can start intervening on them and reminding them about their future goals to help them reach their you know, where they want to get to. So this is a very simple example that was done by my grad student recently. And then even more recently, one thing we have observed here is that this involves modeling the user as an inner loop, right? So we have an agent who's trying to figure out how to nudge the user, and we're assuming that the user themselves is a little agent that is optimizing. So in this particular case, we're assuming an exponential discount factor. And as you mentioned, people are not always exponential discounters. So just at RLC this year, we had a paper that showed that even if people are hyperbolic discounters, which basically, what hyperbolic discounting means for people who haven't seen it is that your discount is like a 1/1 plus gamma or delta. And what happens is that you care about, like, you may have this reversal. Like if I offer you $1 today versus $2 tomorrow, you might say, I just take the $1 today because I don't know if I'm going to see you tomorrow and just want the goods and run. But if I offer you $1 a year from now and $2 a year and a day from now, then you might be like, hey, I'm going to wait about a year anyway. I might just take the higher thing, a year and a day from now, right? It's much more harder to work with mathematically, but we've shown that at least in the context of these sort of nudging agents, we can well approximate the hyperbolic human with an exponential discount factor. By well approximate, what I mean is that the agent will still be effective in giving the right nudges. We don't need to know every detail about the human's planning, but we just need to make sure that the nudge comes out right and we don't bug them inappropriately. All right, so to finish up, today, we don't usually spend a lot of time talking about this discount factor in reinforcement learning. And yet, it actually has a big effect, right? Like if we're planning and we set the discount factor quite large, we may be overfitting. We showed similar things occur in inverse RL, that the choice of this discount factor, which we often just think of as a nuisance. Honestly, when I started doing RL, I just always set it to 0.99 and called it a day. It really affects the generalization in performance and in the human-AI interaction. So I think this is, the set of things that I shared today are not necessarily a closing of like, here's a conclusion, but more of or an invitation of like, what else can we do by thinking more carefully about this one parameter, one-dimensional, only between 0 and 1. Seems so simple, but yet has all of this versatility. So hopefully in this hour, you have had a chance to just escape all the realities of the world and enjoy some fun thinking about this discount factor. All of this in collaboration with many excellent students and collaborators. Thank you very much.
Okay, any question for Finale? Yes. I have to make one. Fernando.
Yeah, just a quick question. Why, like, isn't gamma supposed to be your true belief about what your cost function should be and what you care about it? So, even as a hyperparameter, there is no. So I will repeat so everybody can listen to me. So the question is, why playing with gamma as a hyperparameter and not the true concept of the loss function that we're trying to minimize in this reinforcement learning? And because in a way, if we believe that there is a true value that shows my preferences, then I should be working with a gamma and not treat it as a hyperparameter.
Absolutely. So I think that's a great question. You're pointing out that just like the rewards, the gamma is something about you. It expresses what you care about. But it goes back to the setting where we have limited data. So if we're learning the transition function with limited data, if we're trying to infer the reward function with limited data, we might say, just like we would say that I know that the true function I'm trying to fit is like a 100-degree polynomial, but I'm going to approximate it with 2-degree or 3-degree because I'm going to overfit otherwise. Here also, adjusting the discount factor is exactly like adjusting, this. So as you get more data, yes, you should absolutely, you would go towards your true gamma would be the optimal choice in terms of hyperparameter. But if you don't have enough data, you might say that I'm going to do a better job approximating what you want by actually using a simpler model class of policies. rather than what you truly care about. Oh, yeah.
Hi, thank you for the talk. I was wondering, I have like a question, like I really love like this proposition that you make about the gamma parameter, but I'm missing a bit the context on the states of actions. I'm very used to see this definition. Okay, I have basically my space of actions, my space of states that is of some dimension, and I'm very used to see terms and results that are very dependent on the dimensionality of these two guys.
Oh, yes.
So, so I was wondering how this inference and this on the discount factor is affected by those two dimensions.
Yes, absolutely, that stuff matters. So for example, here in like the theorem, the number of states you have will matter. And the way in which the policy space grows depends on gamma, but also depends on the number of actions. Because if there's only one action, then there's only one, like size of policy class is just one, right? There's only one action you can take, but the more actions you have, the number of policies will grow exponentially. So these things are absolutely in there. I didn't spend as much time talking about those, but these absolutely matter, yes. Everything scales in S and A.
Okay.
Yes.
Hi. Well, a practical question. Let's say if I was thinking on mobile health, and let's say the idea may be if you have a chronic condition, see the problem in the other way around. That is, I want to force high gamma. So
Yes.
how can I design or optimize the action and the reward in order to have? I don't know if there is any work on this problem.
So that's exactly what I was saying with the human. So you want the human to increase their gamma if they have a chronic condition. So they're thinking far enough ahead. They're saying like, oh, I want to keep my diabetes managed, so I want to do my rehab. And they're like, again, we're not on the behavioral side, but they're on the behavioral health side. People have done interventions such as imagine being able to take your grandchildren to the playground. Imagine being at your grandchildren's graduation, like keep yourself healthy so that you can experience important life events for people that are important to you. And that is basically the strategy of trying to increase people's gamma.
But are there any work on how to, let's say, optimize, not from a, let's say, human behavior point of view, from a technical perspective, how to design the reward in order to increase gamma?
Oh, you mean like kind of shape the reward so people think farther in future?
Yeah.
We have played around with this some, and a couple of people have. I think that it kind of goes into these doubly robust off-policy evaluation methods, or that's the way we've been thinking about it, where you can add in a shaping parameter, and the optimal shaping parameter is the value of the policy. So I see that as a potential thing. I think there's still the question, though, the basic question of the overfitting. Like if you're in the inverse setting, like how do you know that the reward is the right reward? But if you do have a sense that this is the right reward and people should be planning over a long horizon, then you can kind of cache it to the present with reward shaping. But also happy to chat.
Following the planned agenda, we have coffee break and posters to socialize a little bit. The coffee break, I guess, is in the canteen in the -1 level, but the posters are on over there. So Patricia will guide you there.
The canteen, you can go downstairs and...
Okay, so let's all follow to the canteen.
Hello? Okay. All right. So, seems everything seems to be working. You can hear me now. The slides are there, so everything should be good. Okay, so this is a talk about a foundational model for macroeconomic time series analysis. And then this is something, and the idea here is try to approach the problem of time series the same way that we have approached the problem of text generation. Right? And in order to justify what do we need this thing, let me start from the beginning. This is a talk that I typically give to economists, so I need to start provoking them to pay attention to me, right? So that's basically the first couple of slides is a provocation towards them, right? Why machine learning is not statistics, right? That's the, so they will tell you, no, machine learning is just a statistic, there is nothing different compared to what we do. There is a huge difference between machine learning and statistics. Even though, when you look from a loss function perspective, we actually solve exactly the same problem that they do, right? We minimize some loss function over our data points, given a model, and we want to make predictions over y, right? And then we assume that we have some data coming from an IID distribution. So economists and machine learning solve exactly the same problem. Why is not the same thing, right? So the idea is very simple. Economists only care about the function, right? And they only care about f of w, right? They care about the parameters. They care to say, hey, how does this model reality, right? Is there any causal interactions that I can get from it? People in information theory also only care about the model. They don't care about the machine learners only care about the sum. The model is only an excuse to make the sum smaller. Okay? And once you care only about the sum, is when we do all the crazy shit that we do that economists will never do, right? Starting with embeddings, over parameterized models, or self-supervised learning. Those things an economist will never do because there is nothing about the model there, right? But if you care only about the sum on some test error in the future, you can allow yourself to do anything in order to minimize that sum, right? And that's the main problem. You can see this, if you don't believe me, just look at these things, right? George Box, all models are wrong, some are useful, right? Everything is about the models, right? The second thing that you have is the definition of machine learning from Kevin Murphy's book in 2006, right? Machine learning is about predictions, right? That's the only thing that we care about, right? So that's the main point from of why we need machine learning. If you only care about predictions, you should focus on machine learning solutions because you're minimizing the error. If you care about what is happening to the world, then you should go the statistics way. So I didn't say that machine learning is better, right? I only said that it's different, right? So there is a place for statistics in this world still, right?
By the way, what do economists say about the IID assumption?
I think the IID assumption, the economists say that there is no IID assumption. In machine learning, we don't even worry about not being an IID assumption. The IID assumption is idealization in case you want to prove theorems. We gave away the idea of proving theorem for anything useful a long time ago. So anything useful, people still prove them, but they have no impact on whatever we're doing, right? So now the next thing is, why do we need foundational time series models for time series? Because the main point when we're doing machine learning, and as I said at the beginning, is we use embeddings, right? The idea is that we take some non-vectorial data, it can be an image, it can be a protein, it can be text, and we convert it into a vector space. Once it's in a vector space, we know that we can compute distances and do all the things that we care about. But time series are already in a vector format. So we shouldn't need any machine learning approach to do those things, right? Any of those algorithms, an autoregressive, a GARCH, a hidden Markov model, any of those things might be good enough for the problem that you're trying to solve, right? So why do we want to go and take the step further? So any of these should be good enough, okay? the idea is not in the model, right? The idea is always in the data. I mean, the model, as I said at the beginning, is an excuse, right? So the good thing about going the machine learning way is like, you don't need to think about if there are nonlinear interactions in the data. You don't need to know how many variables you need. You just expect that if you have enough data, everything will take care of you. The other good thing about a foundational model is that if they deliver on their promise, it means that you can put any time series that you want, and you can do any prediction that you want. And that looks like, oh, Fernando, why are you saying that, right? I'm saying that because of this, right? This, if you haven't read this paper, just leave this talk and go and read the paper. You will learn much more than from me, right? So this is the first paper from OpenAI. Sometimes it's called the GPT-1 paper. And this paper is very, very remarkable because it's the first paper that they published. It's where they found this zero-shot behavior by chance. And the good thing is they don't even hide it in the paper, right? This thing right now is what changed everything in what we're doing in machine learning. You read the paper, zero-shot learning is not mentioned in the abstract, it's not mentioned in the introduction, it's not mentioned in the conclusion, right? The paper is a prototypical paper of NLP from 2018, right? Hey, we're gonna take this transformer architecture, we're gonna use the decoder because Google already used the encoder, we're gonna do the fine-tuning, we're gonna do the pre-training, we're gonna do the fine-tuning, and say, hey, we're gonna try to see if it works by itself. Right? That's what that paragraph says. And then they show this graph and say, hey, it works. The more data, the better that it works. Right? So it was able to do sentiment analysis and question answering as you train it with more and more data. Okay? What I show there is the gap between what the zero-shot capabilities are and the fine-tune on that paper, right? So the gap is 30 points. So it's really crappy, right? It still works. So the idea of the zero-shot is if it works for text, why wouldn't it work for time series, right? I am not the first one to think about these things. Right? There are hundreds of papers doing these things. The interesting thing is that this came for free. It's something that we wouldn't expect, we shouldn't expect, but it still is there. So that's one why we're looking at this model. So given this introduction, let me go and present the transformer for time series, which is this Moria architecture. So today, even though, as I said, there are tens of papers doing foundational models for time series, most of them are for univariate time series. Those models are boring, right? So if you see that there's a univariate time series, don't bother reading the paper, right? The interesting ones are the ones that can use covariates, and that can help you. And there are actually, today there are two. This is the Moria one, which is that Salesforce produced a year and change ago, and Chronos 2 that Amazon published in October, right? The idea of Moria is that it has all of the things that you care about. They have been trained with a lot of different time series, although most of it is coming from energy. It has very little from econ and finance. And it's able to take as many covariates as you want, and it can do it for any time instance. It's actually a bird-like architecture, so it uses the encoding, although it's only used to predict into the future. So it's never trained to predict into intermediate values. It uses the rope positional encoding. That is the positional encoding that is it's a stationary positional encoding, not an absolute one. So it makes more sense when you want to try for time series. Also, the language models use it these days. As I said, even though it's a bird-like, only predicts into the future, so you cannot use it to interpolate. By itself, it's multi-frequency. It can take data from milliseconds 2-year data. So without changing anything in the model, it gives you a probabilistic and it gives you a probabilistic output. So from that perspective, it has all the qualities that we wanted to have. Right? So if this foundational model is there, we try with the data, it didn't work well enough. Right? So the first thing that you find when you're talking about foundational models is that they haven't seen enough data, so fine-tuning for some data is interesting. So what we did is we took this data and we threw all the data that we have at the DAS at this. So we had, I think, is data from 60 to 80 countries, and then we have like around 3,000 variables per country. So the idea is to be able to take this model, fine-tune it, and see if we get some improvement compared to the original data that we have in to the Moriai algorithm. Okay. Just for everybody to know a little bit about the architecture, let me go through it. The model, again, it flattens everything out. So every token that you have as an input, you can put it in any order that you want. And then you have a variable ID that it tells you if you belong to the same time series. So variable 0 is always the same time series. Variable 1, the same time series. And then the time. And then the time, they have to be aligned in time. And then the model masks several tokens into the future in order to make the prediction and learn the embeddings for the time series. As I mentioned, the model is multi-time series. So we'll do the patching of each one of the variables in different chunks. So you can do it from 1 until 228. And usually the idea there is, if you are predicting something in the day or month or quarter, you will use a patch size of 1 or 2, because you don't want to predict much more than that in the future. If you're talking about energy and you're in the 15 minutes or in the millisecond type of, you might go to 64 or 128, because you don't want only to predict one value, you want to predict a significant number of values into the future. All of that is handled by the model by itself. They have trained it, again, I gave you the summary, I think they have 27 billion tokens that they have gathered from Salesforce in order to create the data set. Now there are bigger data sets to do this models. So when we took these things in order to predict the 3 things that the central banks care the most, which is GDP, unemployment, and inflation, the results were not better than autoregressive models. Right? So they weren't that bad, but they weren't better than a simple autoregressive model. Yes? We do fine-tuning. I will show how we do the fine-tuning. That's a secret sauce. Okay? So what we took, again, is this BIS macro data from 80 different countries. As I mentioned, we focus on GDP, CPI, which is inflation and unemployment. And then we made several decisions to fix the model for things that economists care about, right? So the first thing is, even though most of the variables that macroeconomists care are either on the monthly or the quarterly basis, we decided to take a granularity of 1 day. So instead of taking the multi-frequency and the multi-frequency, we say, look, everything is going to be on a 1 day, and we're going to use a token of length 32. And the idea here is, many of the variables that we want to estimate only move with a month or a quarter, but many of the covariates might have higher frequency, right? So if you look at oil prices or FX rates, or you look at the stock market, or you look at surveys that they do, those things come on a daily or weekly basis. So the idea is to be able to say, hey, if I want to do nowcasting, which is understanding what the variable would do the next time that is reported, I want to be able to change the variable on a daily or weekly basis. So we took those 2 decisions, and the idea of doing the length 32 is that whenever we make a prediction in the next token, the value for the variable that we care about will change in that period of time. So that's the first thing. Then the other thing that we care about is we can do forecasting, which is with information until now, what is the value in the future? Nowcasting, with information until now, and everything that has happened until today. What is the next value? What is the predicted value today? And the other one is scenario planning, which is, if I assume that the oil prices will change like this, what will happen to inflation, or what will happen to GDP? Okay? So these three questions are things that economists care when they look at these models. And I will definitely show some of the examples and why the scenario planning might not be as good as we wanted to. Okay. These are what Pablo wanted to know about all the implementation details that we look. So the first thing that we do is we took all the variables that we have, and many of these variables are changing in order of magnitude. So we don't only show the variables as it is, which is the first difference. We show the log, and we show the log difference, right? So for example, the prototypical thing that you will see on inflation, what you see is the log difference, right? And not only that, you see the log difference on a year over year. That's the typical one that the same thing with GDP, that either they show it year over year or they show it quarter by quarter, right? But then there are other variables that you want to have it in the original value or in the first difference. Okay. The way that we train the model is always by showing one of these three variables and 10 other variables from the same country. Right? So we pick a country, we pick 1, 2, or 3 of these variables and 10 other variables to explain the variability. Okay? Then we take information from 4 to 5 years in order to predict. And then we use all the data from 84 until 2003 to predict 2002. And then we left 95, 2005, 15, and 2023 and 2024 as a test period. So we never show any of that data to the model. We mask between 1 and 5 values, so we can predict up to 6 months into the future. The other thing that we did is have this jump mask when we look at the values. And the idea here is very simple, is if we're predicting 32s into the future, but we only have the value every month, the first few values are the same thing that you already observed. So you shouldn't predict that value. Right? You already know that information. So we only predict what happened after the information has been released. Right? And we have evaluated everything with respect to the release date of the information. And we did 2 things that I think are interesting. We trained the model from scratch, and we fine-tuned the model, the original Mori AI model. The training from scratch didn't work. Right? The results were very bad. Right? So the idea is, even though, as I said, we have, at the end it was like 50,000 different time series, that was not enough information for this model to learn. Right? And the information that we got for Mori AI was good enough to get enough information to put the model into a good place. Okay? Questions, comments? Clear enough? Good. So let me go over the results, right? This is just to show you a little bit of how the model generates results. So this is the inflation from the US. The blue line, so we condition the model on all the green line, and you see the piecewise constant because it's on a daily basis, so every value is held for 32 days, and then we predict 2 years into the future. The blue line is the true inflation, and then what you have there is 100 different samples in which you can see that the first thing that you see is that the model behaves like we want it to behave. So it's more or less around the values that we expected to see. Sometimes the model might overshoot the values. And this is a very high inflation. This is on a month over month. So the year over year of this inflation is around 8%. But most of the values are within the range that we expected to have in here, right? So this is just a sanity check to show that the algorithm does something reasonable. Okay? And then I'm going to show you two different things. One is the forecasting. The forecasting is just to show you that the algorithm works, right? That is the only one where we can check the ground truth. So we can tell you, hey, these values make sense, right? And we do the forecasting in 3 different scenarios. One is the variable by itself, purely autoregressive. We give them 5 variables to estimate it from, and then another 5 variables, extra variables in order to do these things, and then we estimate GDP, inflation, and unemployment. And the second part is the scenario planning. And this is just an illustration that there's going to be a variable that we care about that finish on a given date. And then these are the values that I want to estimate. And then I'm going to take this covariate, that I'm going to take it until the day that I know. And then I'm going to make up values to say, hey, if this happens, what will happen to the economy? Okay? So let's go first over the GDP estimation, right? So the GDP estimation, what you see in here is what happened when we estimate the GDP 1 quarter ahead or 3 quarters ahead. The first table is when the values are non-seasonally adjusted, and the second one is when they are seasonally adjusted. And what you can see in here is the first, let me go, the top, this is the original Moriai, and this is our model, right? When we do it in an autoregressive manner. Right? And then what you can see here in the Moriai is that compared to our model, is that in the seasonally adjusted is equally good. But when we go to the non-seasonally adjusted, the Moriai really does perform much worse. Right? So it's not able to do. And I'm not going to show it here today, but when you look at the confidence intervals, they clearly go off rails, where our confidence intervals are where we are supposed to have them, either in the seasonally adjusted one. And then what you have in the third and fourth and the fifth and sixth are the results when we add the basket. Right? The first thing that you can say here is that by adding the covariates, we don't get a lot of improvement. Right? This is a prototypical problem that happens in most of the problems in economics, in which the variables tend to be well behaved, and an autoregressive model tend to be good enough. So you don't need to do much more than an autoregressive model. Right? But that doesn't mean that sometimes the differences and the subtleties are important to see, hey, what happens if this variable is in or is out. So it's more the difference when you're trying to make a prediction. And all of those errors are relative to the autoregressive of order 1. Right? So if the values are below 1, it means that they are better than the autoregressive of order 1. If they are above 1, it means that they are worse. One thing with respect to best and worst that I think is very important when you think about these models. There are many papers out there in autoregressive model that say, hey, this is better than any other model that is out there. You shouldn't be using any other econometric model. I think that's the wrong approach to this problem. I think a foundational model should be a sensible model to work with, but it's never going to be the best model. If you dedicate time to think about the relations between your variables and construct the right econometric model, you will beat any foundational model. Right? And it shouldn't be difficult. So a foundational model, you should see it as your friend when you're trying to do some quick and dirty solution. Right? It's something that say, hey, I'm looking into this problem. Can you tell me what is the relation without needing to train a model? Right? Like asking a ChatGPT, hey, should I go out with this person? Right? Right? You describe the person, you tell her like good things and the bad things, and then it will give you an Don't take that output as the thing that you should do, right? So the same thing with this model, right? Take it as something that might give you an advice, but you should probably work harder. Right? That doesn't mean that sometimes you need something quick and say, hey, there is some relation in here, and that can help you. Right? That's the whole point of the model, is to give you something to start with and not the end of your journey if you really care about that problem. If you're just trying to finish your homework, then you can use this. Right? That's no problem there. All right? So that's the first thing, is because the results of reducing the error to 50% is impressive in many of these scenarios. But we didn't try to get the best econometric model that we could. Right? So I'm sure that you can get to those values without working very hard. And this is just to show you in a different format. These are the results for inflation, and instead of showing everything aggregate, we show you for any of the OCDE countries that you have, right? And then what you have is the red line, it will be 1, so there's the, and what you see is that most of the values are below the line. Again, that is not the point. The point is that even when you look at all the distribution of errors, none of them go very, very far. I mean, I don't want something that the mean is very low, but that the variance is huge. So that's why, to show these things, and even for every country, things tends to be more or less reasonable, right? So this is the forecasting. So the forecasting, when we have tried for this type of variables, tend to work. We have also tried to, with other variables in which they are not in the training set, something that the Swiss National Bank is doing with data that is actually, so they are looking at GDP and inflation, and they use data that is non-common. So for example, how many flights arrive in the airport of Zurich? How many trains are going through the tracks? How many construction equipment is being bought or used throughout? And that way can give you some other variables that are not typically used. For those models, it also works. It's not better than the model that they created, but it gives you a reasonable result. Now, let me look into the future type of predictions that that the model has. So right now I'm going to let the model riff in the future for 2 years, right? So the question that and these are the kind of things that we are used to ChatGPT being very good at, right? So when you ask something, it's able to generate something that is grammatically correct. Right? Doesn't need to be true, doesn't need to be correct, but it's grammatically correct, right? So what I'm looking to here in our model, which is this column over here, is that when you look at the inflation values, it's grammatically correct, right? It's giving you something within the inflation values that you would that you would expect. And then what you have in here is the autoregressive model. The difference between this model and this model is this is the autoregressive model in which we add the noise variance to the predictions, and here when we don't add the noise variance to the prediction. And if you look the autoregressive model, basically what it's telling you is like, I'm very confident that the value is more or less constant and everything else is noise. Right? While our model is able to balance those two much better than the autoregressive model. And that it makes it more useful in the predictions that it's giving you. Because telling you, hey, no, the inflation is around 2% with plus minus 8, okay, I knew that already, right? So it doesn't give you much information. Yes? As I told you, I cannot hear you, so. So the thing is, so just to, I didn't tell, right? So in this one is an autoregressive. This is for inflation. I will look for it right there, but this one is conditioned only on the autoregressive, and these two have different values in which you are conditioning on, which again makes sense with the things that we were talking about, because it changes very little from one to the other, right? If you look at the autoregressive, and then the variables here are the same per row, right? And then what happened in here, you can see is that once you add the additional covariate here, it gives you something that is more reasonable than what we have over there, right? So that is just to show that is not only the horse race of how good you are in estimating, is what are the confidence interval that is giving you, and what is the information that you can gather from that model. And this is where the scenario planning starts being interesting for economists, right? So this is, again, this is the inflation in which we condition on the oil prices for 2 years, right? So the blue continuous line is the true inflation for these 2 years, and the different lines are what the model believes, depending on the condition of the oil prices. And the result is very, very interesting, because the first thing is the blue line here is if we condition on the true values for the oil, right? The orange is if we take a 3% reduction every month. The green is +3, +5, and +9, right? So the thing that you see with this model is, first, is that all of them are ordered, right? So without any information that we're giving it, all of them are ordered. So that's a good thing. The second thing that you see is that you have a non-linear effect, right? And one thing that is very important is the oil prices on those years was mostly constant but went down. So the orange line of the oil prices, the barrel of the petrol went very, very down, right? And then what happens at some point is that once oil prices go down to 0, that they don't get to 0, it shouldn't affect inflation. So that's why the orange and the blue line converge. Right? There is at some point that they don't have any effect on the... and the other thing that you see that is very interesting is the purple line, that at some point start taking off much higher than the others, and this is because we were so aggressive that the oil price went over $200. Right? And in that case, you will say, hey, we will expect inflation to be significantly higher. Right? If we do this experiment in the 70s, it will be significantly stronger, right? But we don't have high quality data from the 70s today, okay? High quality data studies in 84. So that is also, it shows that it's time dependent in this model. So from this perspective, the relation between inflation and oil prices is very clear, right? The higher the oil prices, the higher the inflation. There is nothing that should surprise anybody there about that, but then it tells you more or less how much do you think that this model should suffer from those things. So it's not important to match the values, but to say, hey, if this is what I believe oil prices will do into the future, maybe you can do something a priori to try to compensate for that. Okay? Now let me show you something that is even more interesting. Okay, which is, instead of conditioning on oil prices, we condition on the interest rate of the Federal Reserve Bank. Right? And we give them 3 scenarios. The current scenario, one in which the rates didn't go up as high and start going down sooner, and one in which they went higher and didn't go down lower. Okay? Do you see any difference? Right? So clearly that doesn't work. Or it's doing what it's supposed to be doing, right? Because the model is not a structural model that predicts what happened to inflation. It's a correlation model, right? And the causation from inflation to interest rates is the other way around, right? You increase the interest rates because inflation is going up, or you decrease the interest rate because inflation is going down. So by giving the interest rates, the model should tell you, look, you're not giving me information. Right? So the model, in a way, is telling you, I don't have enough information. The only thing that I'm going to do is the autoregressive model that I know how to do. Okay? Just for completeness, these are the 3 interest rate scenarios that we apply, which are very different in each one. Right? So it's not just for a lot of you to have it. Okay, so if the causation goes the other way around, let me ask the question in a different way. Right?
let me give you what is the inflation that I want, and let me ask you for what the interest rate should be. And just before I go into this, I'm not telling the Jay Powell that this is what he should be doing at the Fed, right? We have Trump for that, so I'm not gonna go there. And this is what you get, right? We get the inflation, and then say, hey, give me the interest rates. And we were at the beginning working with very little data, so we were only looking 12 years into the past. And what it did is that it took the interest rates and it put them down to 0, basically, or 1. Okay? It has some persistence, but it put them down to 0 because that's what it has, right? But inflation wasn't coming down that fast, right? Why is it doing this? Because if you go back to 2010 until today, interest rates have been mostly 0 in the US most of the time. And the interest rates weren't focusing on inflation because inflation was low, was focusing on employment, and you have quantitative easing. So there was no relation between the two of them, right? So basically it's telling me, oh, if I have to predict interest rate and I look at the past tells me 0, so okay, let me move it down to 0. Right? So then we say, hey, let's go back to the 80s where the interest rates were higher, the inflation was higher. And then it gives you something that is very reasonable, okay? Which is more or less is for the first few quarters into the future, it gives you the same value that the Fed did, and then it put it a little bit lower, right? But then all of those things will depend on other conditions, right? But it doesn't go completely haywire. In any case, this is a correlation analysis of what happened in the past. It's not a structural model that you should know what will happen into the future. And this is gathering information from the 80s and 90s, right? And maybe the economic conditions are very different from what we have in the post-COVID inflation. So this is just to show that these models are only correlation machines. Right? There is no causation. There is no intelligence. There is nothing useful from if you want to learn about the causality of what is happening here. Okay? So this is just to say that also applies to your ChatGPT. Right? It's only doing correlations to whatever you ask and trying to please you. So this is the same thing, right? It's just trying to please me and give me what I want so I can give a nice talk. Right? But that's the only thing that this is trying to give you. Just to show that things change, if instead of conditional inflation, we condition unemployment, that was a little bit higher, what it does is it puts the interest rate a little bit higher. Sorry, the unemployment was a little bit lower than in the 80s, so that's why it leaves the interest rate a little bit higher, right? Because you're not that worried about unemployment being too high, right? So in that sense, it's also sensible in the thing that that is doing. So this is the last slide that I have. One of the things that I like to tell when we finish, first, there is a GitHub page where you can download it, play with it. I want to know if you find something that it doesn't work. Right? If it works, I'm happy for you. If you say, hey, Fernando, it's not working for this, let me know. Because what we're trying to do is, this is a foundational model for macro, right? One thing that we show is that the MORI is not good enough for this data and this type of analysis. So you need to do the fine-tuning, but we still want to be something that is good enough for any macroeconomic problem. And then the project NEO data is the one that I mentioned before with the Swiss National Bank of using non-common variables in order to predict the value. So this is it. Thank you.
Is this working? Okay. So thanks, Fernando. Have two questions. Okay. One of them is about the design of the covariates. Have you thought about using like some sort of LLM to create embeddings for the news and the kind of like the news extracted from newspapers and the economic discussions in forum to condition the model for the future? Okay.
I mean, people have thought about that. So when you try a foundational model, you're not trying to solve every problem that is out there, right? So as I said, I'm old, right? So time is limited.
Okay.
There is a lot of economists that have been using either news from I mean, right now it's getting very expensive because all the economic journals ask you to pay a lot of money to have access to the news. But there is people taking the news, using any language model to embed them. Then you put an autoencoder to reduce the dimensionality, and then train that jointly for the time series. So you can do that type of information. And then there is people, the other thing that people are doing is, I think the ECB is doing this, is web scraping the prices that companies are putting in their pages and using that as an early warning of the information that you can do. The good thing when you have embeddings is that you can do anything.
Sure.
So it's just, do you have the time and the patience to gather the data?
My second question was about, because it seemed to me that most of your evaluation of your results, at least you put it in terms of qualitative, this time series makes sense, goes up and down and such. I don't know if you can rely on these arguments to do a fine-tuning that is more closer to reinformer learning type of tuning. So someone that knows more or less about the context can say, okay, this prediction makes sense than this other, instead of fine-tuning just by predicting the next values, just fine-tuning by agreeing that this predicted trend makes more sense than this other, sort of.
I disagree there. You are focusing on the way that I present, not on the way that we work on the paper, right? Most of the time was dedicating in generating that table, right? So the only way that, the way that we train these things is in a supervised manner in order to do the forecasting scenario. That's the way that we train this model.
But do economists care more about point-wise number or tendencies?
So right now we train the model to care about predictions, right? That's what I said at the beginning. Sure. As a machine learning, I only care about predictions, right? Now, once you have trained this to make predictions, and given that I'm going for the foundational model, what other things I'm getting that we didn't have before? And then the comparison about this qualitative analysis that I'm doing is just, the first thing that I want to do is that it gives me something that aligns with reason, right? So the predictions make sense, the confidence interval makes sense. Whenever you put different variables, the ordering makes sense. The next thing will be, and this is the evaluation that we still need to do, is if we do a structural prediction, like the economists do when they look at these models, how does it compare to those structural predictions? And we still have to do those things.
Hi, Fernando. Thank you for the great talk. My first comment is related to the first thing that Pablo commented.
The answer will be the same then.
Yeah, but it's more like a suggestion or something that the model, the foundational model, reminded me a lot of what is called prior fitted networks, PFNs, and it's something like it's getting like quite a hot topic in the recent years. Prior fitted networks, it's called PFNs. And the motivation is different. They want to build some universal predictor for tabular data. So you train a foundational model on many, many different tables with completely different variables and metadata and transformers. And the goal is to universalize the prediction. So you just tokenize the different variables, use as inputs to a transformer, and the transformer just needs to do predictions to whatever the variable you want to predict. Then here, so this model is even more flexible because you integrate, you incorporate time, the notion of time, and actually that's going to define your prediction task, forecasting, nowcasting, etc. But why it's related is because in these models, it is so important to use embeddings of the metadata. So you might have different tables with variables that has completely different metadata, and you are feeding to the model as different variables, but they can be both related to blood pressure, heart rate, and just have different names. So the model has a way to find correlations, and I'm pretty sure I could expect that in econometrics you can find variables from different sources that they are super related and they can be integrated in the model somehow. So what people is doing is, for example, feeding your metadata, the name of a variable, to your LLM that gives you a vector, and somehow you combine or you can concatenate it to the token. Something like that can work. But what I read is this is quite important in these models. So I don't know if that could help here.
So let me give you two answers. Yes.
Yeah.
The more information, the better. So I'm not gonna. But if you're going for universality, then you need to make sure that, because if every new time series that you created doesn't have a label within the training set, then it gives you no information. Right? So the goal of not putting the metadata and the name of the variables makes sense. So for us, that would be one of the arguments. For our case, probably that will help. Is look, I'm gonna say, this is inflation, this is unemployment, this is GDP. We can definitely do that. The other part of why you might not want to do that is the same problem that you have with the current LLMs, right? When you train an LLM today, you're trying to teach them two things at the same time. You're trying to teach them English or a language, and you're trying to teach them facts, right? And that's when they fail, because you're trying to teach them so many facts that they don't fit. And that's when they hallucinate and they do all of those things. So the solution to that problem has been, no, let's take the language model only to learn simple facts and language, and then give them access to tools to find facts, right? So instead of generating Python out of as a freewheeling, it will generate the code, it will open a terminal, it will run the code, it makes sure that the code runs, and then give you code that runs. That doesn't mean that the code does what you want it to do, but the code will run, right? For the time series, what does it mean in this case? I want the model not to catch your data about facts, but about correlations between the data. And that the facts, if I care about time series analysis, should be containing the prompt, which is the history that I'm giving it. So I might not want the model to have facts, because I want the in-context learning to be the only one providing facts for my prediction, right? That, as I'm going circular at the beginning, I still believe that if I add the name of the variable, I can do better. But that, because I'm adding facts to the model. But from a principled way, I might not want to add facts.
I see. Thank you.
Hi, Fernando. I was really, really happy and hyped at the beginning of your talk, and at the end I was a bit like down. Yeah, I was curious, like, that you did. I was surprised that you didn't talk about time resolution somehow, like in this and the size of the context that you are using during training. I know that in the end you had made this reasoning about the causation and how I agree 100% that these are correlation models. But I don't know, I'm very curious, like in an LLM it's very obvious that the grammar looks very nice because probably in the short-term resolution between tokens things make sense, and maybe in the long term it's just a disaster. I mean, it can, for coding, it can do very well. I mean, I'm not an expert in LLMs. Can do very well like a for loop prediction, but in the long term the entire code is crap or does not work well. So I was curious here if in this work you have explored this problem, and how do you, because my feeling is that for language kind of you have time resolution that is very important between tokens that are close, and you know, as long as your context is longer and longer and longer, it's a bit of a disaster. And I don't know if that, you know, you use BERT and you use kind of a similar architecture. I don't know if you have the same case here in economics. I don't know what is important in the time resolution in economics. Like you have, I can feel that you have short-term and long-term features very important. This is the question. Yeah.
Okay. So one thing that is important, right? In here, we use 12 years of context and 37 years of context. During training, we only gave it up to 5 years of context, right? So we never train with 13 years, we never train with 37 years of context. So that's one of the good things that you have with this, the rope embedding that you have. The rope positional embedding basically makes sure that the positional embedding depends not on the absolute position of the time series, but on the time difference between the two of them. So, as I mentioned before, the whole point is that I'm trying to learn the language of time series, not facts. So, by showing it shorter, allows me to understand sufficiently of the stationarity of this problem in order to be able to capture those relations. Then when I do my predictions, whatever is the in-context learning, whatever the prompt is, the history that I'm giving should be the one that is more determinant of what is going to happen in the predictions that I have. Because if you think about this problem that you are estimating a model, what you're using to estimate the model is the past data, right? So if my predictions depend significantly on whatever I put into the context, the model is doing what I want, which is that by in-context learning, I'm getting a sufficiently good enough prediction for this model to do what it does. If history didn't change, then the model is just dumb, and it's just using the weights that it has and the facts that it has in order to do the prediction, because it's only focusing on the latest values. So, could we, instead of using 5 years, have used 10? Yes. If we have done only 1 or half a year, that might be too little, right? Where is the sweet spot? I mean, like everything, you try something, you're happy with the results, you don't question it.
You don't think that we change things a lot, like playing averaging over this length?
Can you use them? Because
Sorry. You don't think that the results will change a lot playing with this length of the context and will fix some of the problems you're facing?
So I think that will only, so in economics, I don't think it will change a lot. You don't have interactions that are 5 years into the making. So most of when you look at this and you predict variables into a year or 2, they are usually just go to the history mean, and that. It's like the same way that if you go to weather, right? We know that we can predict weather up to 10 days. After that, historical mean is as good as your predictions, right? And then when we're using machine learning to do weather predictions, what is shown is that it gets better in the medium term, in basically the 6 to 10 days. Because on the next day or 2 next day, physical models have enough information. It's just when the physical model is not clear enough what you're trying to do. So for this, might not be the case. Now, if you go to energy prediction, there may be longer term correlations that happen throughout the week or the month. And if you're doing 15 minutes type of predictions, you might be better off with a longer time series. So you need to think about it. But our original idea of 5 years was to make sure that we had enough from the economic analysis. And we haven't found evidence that that's not the case.
Okay. I have a curiosity and a very practical question that it is. Okay. I don't know much about economics, but about the time series in. Okay, but about time series in health. In this situation, you have real multi-scale time series. Let's say you have some data that is yearly, or that is monthly, and there is only, if you are interested in the short term, let's say minute, hour, or days, there is any more or interesting approach that using upsampling the data that is long term, because the model, it doesn't accept by nature or directly time series that at a different time scale.
Well, the model works on a daily basis, right? So everything has to be converted into daily. From a macro perspective, the daily is too short of a time scale. Most of the things move on a monthly basis. The idea of doing the daily was to try to use other variables. So from that perspective, the way that we're doing the different time scale variables is just by repeating the last value that we have, and that seems to be working fine in order to accommodate time. Again, the values are only plus, it's 30 days, it's not more than that. And the structure is very repetitive, so the model learns that. Although we make sure that we move the values so the jump doesn't occur always on the same split.
Any other question from the audience? Okay, let's have Fernando again.
Okay, so this is the end of the agenda, of course. You can keep on with informal discussions. One minor thing that Patricia told me about, if you love the hangers, you can keep them for sure. If you're going to throw them in the bin outside, just give them to us so we can reuse them for some other event. Okay, it's a minor thing, but well, they asked me to do. Okay, so, thank you very much for your attendance today, and we're going to be interested in your feedback and your interest in organizing similar events in the future. Thank you very much, and thanks for the speakers.